Hello, welcome to the fourth wonderful video of this series, and hopefully you guys are enjoying these, and hopefully they're helpful. This is going to be our first full graph analysis we would have done in class if we didn't have so many problems going on at school with snow days, etc. So hopefully you can follow along, and this is one of my favorite graphs. I actually do this graph in advanced functions as well, and we even talk about what are the limitations of what we could do in advanced functions and not. So here I'm going to actually use red, I think, to write out the steps. So step one is always x-intercepts and y-intercept. Okay, so hopefully you can follow along. The x-intercept, of course, is when y equals 0, and that means the top is 0. I'm going to write that for some of you that would benefit from that. Y equals 0, comma, top equals 0. A fraction is only 0 when the top is 0, which means that x is 1/4. Hopefully you can see that. If you put a quarter in here, they'll make the top 0. So there's y-intercept. And just for emphasis, that's worth a mark. Y-intercepts. Y-intercepts occur when x equals 0, because of course you're hitting the y-axis. So what happens when you substitute x equal to 0 in? You get -1 on the top over 0. Ooh, that means there is none because there is something else there. You can't have -1 over 0. And for those of you that are clever, you will know that there is a vertical asymptote. Check for vertical asymptotes. I didn't mean for writing all of this in red. That's when bottom equals 0, i.e. x equals 0. So you can see that the bottom equals 0. And because we want to do this in order, we should also check out the limits as x approaches 0 from the left and from the right. And this should seem very familiar to advanced functions because you did this in some form or another. And in my classroom, I tell my students, okay, I'm not thinking right now, I'm just writing a bunch of junk. This is like a template. We know for every asymptote, vertical asymptote, the function takes off to infinity, but we just don't know if does it go up or does it go down. So this is literally the little template I'm going to use. And when you go from the left, you're talking about numbers like 0.1 negative. Okay? And here you're talking about numbers like x equals 0.1 positive. And what happens when you put in those numbers? So if you look up at the top here, notice the bottom is squared, so the bottom's always positive, so we don't have to worry about that. If you put 0.1 positive in here, 4 times 0.1 is like 0.4, take away 1, that's negative. So this is negative here. That means it's going downwards. If you put in negative 0.1, that's negative 0.4 minus 1, that's negative, and again the bottom's always positive, so that's also going downwards. So we now have an idea of what that looks like, going downwards. I'm debating whether or not we should start drawing the graph right now or if we should wait till we have all the information. I think we're going to wait. Next, horizontal asymptotes? Question mark. There might not always be a horizontal asymptote. Now, in my classroom, I try and tell my students the horizontal asymptotes occur way, way, way out at infinity. So if you take a look at the function, you look at it and you ask yourself, when x gets really, really big, who's the boss here? And as you can see, the x squared on the bottom is the biggest power of x. It's the boss. So as x gets really, really big, the top is going to become insignificant. The bottom is going to grow way faster. A quadratic grows way faster than a linear when x gets big, like a million. So we know that the bottom is going to dominate, and this one is going to actually have a horizontal asymptote at y equals 0. In other words, yes, it does have one. So they don't always have one, so watch out for that. And I called this boss on bottom. You don't have to call it that, but for my students, I noticed the boss is the biggest term is on the bottom, so it's going to drive the whole function down to 0. And like the previous question, we should take a look at the behavior around the asymptote. So as x gets close to negative infinity, what happens? And as x gets close to positive infinity, what happens? Okay, and I think you can see that they're both going to approach zero. So I'm not even doing anything earth-shattering there. But it would be really nice to know whether I'm approaching zero from above or below the asymptote. So here's where you sub in a giant number like 100. And zero is the easiest asymptote to approach because in this one case, all we have to do is look for whether it's positive or negative because bigger than zero is positive. And if I put a million in here for x, you get 4 million minus 1, which is positive over positive. So this is definitely a positive. So you're approaching from above. And if you really want to, you could sub in x equal to 100 and then see what you get for y. And it will be positive, so it's going to be bigger than 0. Okay. And over here, you could sub in negative 100. And again, I think you're going to find in this case that you get 0 from below. Let's just be consistent here. Okay, so if you put in negative 100, the top's going to be negative 401 over a positive, so it's negative. So this time we're approaching from below. I strongly encourage you to plug these numbers in your calculator if you have any doubts in your mind. And all you're doing is literally seeing if the function is above y equals 0 or below y equals 0. Um, and this works, the substitution method works if your asymptote is at y equals 1 or y equals pi or root 3. It just gives you an idea whether you're above or below the asymptote. Okay, so there we go. That stuff actually is in a different form, but it's from advanced functions. Whoopsie, believe it or not. Okay, next, derivatives. Now, in your homework and on the test, I will probably give you the derivative for the big graph analysis question. For the simple reason that I don't want you messing up the whole graph because your derivative's wrong. So we're going to do the derivative here, and I'm going to try and go through fairly quickly. Derivative of the top is 4 times the bottom minus the top, which is 4x minus 1, as the derivative of the bottom, all over the bottom squared, so it's x to the 4th now, which is equal to 4x squared minus 8x squared, and I gotta watch out for those negative signs, 2x, yeah, just 2x, over x to the 4th, which if you simplify here, you're going to get negative 4x squared plus 2x over x to the 4th. And I see some stuff happening here. If I take a negative 2x out of everything, I'm going to get a 2x minus 1, I believe. Check that if you don't believe me. I think you're going to get negative 4x squared and positive 2x. Yep. And probably the trickiest thing here is that one of these x's doesn't actually exist. That x divides out, and that actually becomes a 3. So you can see why I would give you the derivatives for these ones on a test, because I don't want you to make a mistake there. And we still have to do the second derivative too. So one of the things I'm going to do before I proceed, actually, you know what, we'll do it right now. Y prime equals 0. And by the way, I forgot to mark this as step 4 using the derivatives. Y prime equals 0, and x equals a half, and y prime is undefined when x equals 0. This should seem familiar like the other questions. We want to know when this thing is hitting 0 or undefined, because that's where special things are going to happen. Things are going to switch from positive to negative. There'll be mini-max points or points of inflection, etc. Okay, now before I proceed here, I see this is in factored form, which was good for me to get to there. But to do the derivative, I'm actually going to keep note that this one here, I could have divided an x out of there. So I could have had negative 4x plus 2 over x to the 3. Divide everything by x, which is legal. That is actually the same as this if you expand that again. And you know what? I don't want anyone to be confused, so I'm going to write that down here so that nobody has evidence that I did that. And I'm going to get rid of this. Okay, so now we do the second derivative. Once again, don't be overwhelmed. We're going to give you the derivatives on the test and on the homework assignment too. Okay, y double prime equals the derivative of the top times the bottom. By the way, doing these derivatives is good practice, for sure. Minus the top times the derivative of the bottom, all over the bottom squared, which is x to the sixth. And if you simplify this, be careful, that's actually going to be plus 12x cubed, and then a minus, so it'll be minus 6x squared over x to the sixth, and that gives you 8x cubed minus 6x squared. And this is a little bit tricky because what happens is you get this x squared that comes out, and it looks like it's actually we take a 2x squared out of there. Let's take the 2 out. 2x squared is in common, so you're left with 4x, I think, minus 3, and over x to the sixth, and then that gives you 2 times 4x minus 3 over x to the 4, because we have to divide out the x squared. So I'm running out of battery, so y double prime is equal to 0 when x equals 3/4, and it's undefined at x equal to 0. Okay, so then what you're going to do is you're going to make a chart using all this important information. So let me see if I can remember here. X, Y. This time we're going to have everybody in the chart. Oh, shoot. Undo. Trying to go fast here. Okay, so for the original derivative, our important points were at 1/4 and 0. So we have 0, we have 1/4. There was an important point at a half and also one at 3/4. At 0 is on the bottom of all of these, so it's actually u, u, u. It's infinite. That's a vertical asymptote, which I think we knew. The first function was 0 there, the second one here, third one there. And what we're going to do is we're going to sub in some points. We're going to do it fairly quickly because I am running out of power. I'm going to start with y double prime because it's sitting right here. If you notice the bottom's always positive, if you put in a number bigger than 3/4, like a million, the top's positive. So this is positive, and everything else on this side is going to be negative because the only sign change occurs at that point, 3/4. For this one, notice here the bottom is not always positive, but let's put in a giant number like 100. So the bottom's positive, this term is positive, but we have a negative out in front. So this one's actually negative out here, but it switches signs at a half and it becomes positive, and it stays that way out here. If you don't believe me, let's try and put in a giant negative. So a giant negative makes the bracket negative, and the front's negative, and the bottom's negative. 3 negatives. Oh, hang on a second. Let's make sure we got this right. Oh, at 0, this might change. Let's check it. Good thing we did. Negative on the bottom makes the bottom negative, negative, negative. 3 negatives. So there you go. That is proof why you should check. This is actually negative. And finally, for the original function, the bottom's always positive, and it's 1/4 that's going to be the deciding factor. So if you put in something like 100, it's going to look a lot like the second derivative. It's positive over here and negative everywhere else. Okay, so I'm going to go up here very quickly, and I'm going to draw this graph. Okay, and we've got a vertical asymptote here. We know from our arrows that they both go down. We also have a horizontal asymptote at 0, I believe. And we're approaching from below and above. So this guy here, so this is y equals 0, this is x equals 0, and this one was from below, so it's just going to look like this. This one actually was approaching from above, so that's kind of funky. We had an intercept at a quarter. Okay? And now I'm going to read off my chart. This right here, plus 0 minus, that's a local max. And this minus 0 plus in the second derivative, that's a point of inflection. So what have we got here? We've got below decreasing concave down like a frown. And we have below increasing and concave down like a frown. So it's going to go up like this. And then at a quarter, across the axis. At a half, I'm above increasing and concave down. Then I'm maxing out, and I'm above decreasing and concave down. And then I inflect, and I start curving up. So at the end, I'm above decreasing and concave up. So my graph's going to look something like this. And approach. This point where I changed concavity is 3/4. This point where I reached the max is at a half. And what we couldn't do in advanced functions was find this height. To do that, we sub that into the original function, which is 4x1 minus 1 over x squared. So when x is a half, you get quickly 1 over a quarter, a half squared. So I think that's 4, if I'm not mistaken. Let's try that one more time. 4 times a half is 2. 2 take away 1 is 1 on the top. A half squared is a quarter, and there you go. So there is your full graph analysis, and we did it before my battery died. Hope that helps. Wonderful day.